Hi, everybody. Craig Stevenson here, president and co-founder of the Oros Group.
And I'm Beth Eckenrode with the Oros Group.
Hi, everybody. I'm Matt Bowers, Director of Building Science with the Oros Group. Happy to be here today.
So we're recording this for those of you that didn't have access to the webinar we did, sponsored by 3C and Passive House California. Jay Gentry, with his great and robust network in California, put together a terrific webinar. Unfortunately, it wasn't recorded as we were doing it, so we've come back and we're re-recording the session for anybody interested in following up on our discussion about the power of existing buildings. So Craig, go ahead and take it away.
Thanks, Beth. And also I wanted to say a thank you to 3C and to Passive House California for this opportunity. Let me share screen here and kick us off. All right. So Oros Group. Oros Group is a organization focusing on building decarbonization. And to do that, we focus on building science and data science and merging the two, which gives us the ability to operate buildings at these levels of performance over 50 years. So Beth and I wrote a book last year called The Power of Existing Buildings. And this won a national award. And this really outlines everything you're going to see today from us. We want to walk you through a case study of a project that we did in Boston that we used the building science. When we say building science, we're talking about really sophisticated, highly calibrated energy modeling to develop a decarbonization plan for a 350,000 square foot building. So with that, let's get started. All right, so we believe that the solutions to building decarbonization requires the merging of building science and data science. What does that mean? When you talk about building science, we're talking about passive house standards, envelope first efficiencies, using models, using technologies, because we're looking for the 1 + 1 that equal 5. And you can only really get that when you're in a modeling environment. You can't put thumb in the air and kind of find your way there. The data science side of this really gets at dashboarding and meters and sensors in a building. And when we merge these two, we can export from the building science or the modeling software hourly predictive data for future performance for all forms of energy, indoor air quality, and BAS parameters. And now we give a higher level of context to data science. So we're going to jump into that in a few seconds here. But first, we wanted to talk about this strategy that we mentioned in the building science, this envelope first strategy. Why do we do that? The cheapest form of energy is the energy we never use, right? So we want to go after an aggressive load reduction strategy. We want to reduce our loads as much as possible based on building science. And what Passive House tells us is the climate-specific thermal barrier for our envelope. We want to create an envelope that keeps our energy in our building so we don't have to keep rebuying it as we push it through our walls. So when we say passive first, we're talking about as much load reduction as possible based on building science. Active second, we want to decouple our HVAC systems and solve ventilation with one strategy and heating and cooling with others. Why? Because heating and cooling strategies at these low loads become affordable. These solutions like VRF become affordable, and code-based solutions, they would never become affordable because they're just simply too large. But it opens up opportunities really to look at active solutions much, much differently than we do in code-based buildings. And renewables last. Why do we want to do renewables last? Because we want our photovoltaic array to be this big and not this big, right? This is the natural order of sustainability for building decarbonization. The Passive House Accelerator is an organization of practitioners that have been doing this for a long time. And they come at this in a slightly different way, but really using the same philosophies, the same logic, right? They want to also use passive house strategies to first bring out as much efficiency from these buildings as we can. And then they want to electrify everything and then use clean energy to offset that. And that's how they get to zero carbon. It's really the same methodology and the same thought. We want to electrify everything because we cannot offset fossil fuels like natural gas. We just can't offset them. Once we use them, they're done. But if we start to electrify our building, we can use the photovoltaic array on our roofs or on our grid to start to offset that consumption of electricity. And that's how we get to zero carbon. It's the same methodology and the same strategies as I outlined in the natural order of sustainability, but it's just shown in a slightly different way. So What we're going to get to today is we're going to talk about a case study for a project that we're doing in Boston. And we got a call from them in Boston, said, hey, I've got this building in Boston. I know I'm facing a fine for BERDO, which is the local law up in Boston for building decarbonizations. And I don't know how much I'm going to be getting fined. Can you help me? Sure. Yeah, we can do that. So we basically sit down with them and we walk them through the existing performance of their buildings and how that is viewed against the context of the regulations. And then the next question we get asked, obviously, logically, is how do I mitigate? That's what we're going to walk you guys through today. So we want to basically show you how we can do this for existing buildings. New's easy. We do new all the time. Just build a better building. Existing is more difficult because it has constraints. And those constraints are, massing and orientation is already set. Window to wall ratio is already set. Sometimes thermal bridging is already set. So we need to basically work around those constraints to develop the highest performance building we can get pre-renewables. And that's what we're going to do today with you guys.
Yeah, so thanks, Craig. So let's get started first by kind of giving an overarching idea on how currently buildings are being decarbonized, right? And the method that's being used is comparisons, right? We're going to compare the existing building to other buildings, other similar buildings, maybe in the same location, maybe not. And we're also going to compare the building with how it performed like the year before, or maybe if you're lucky, you can get utility data that's accurate for the past 5 or 6 years. But the trouble with that is we're also coming out of a pandemic, and building occupancy and electrical usage is going to go up to pre-pandemic levels. So using the previous year's worth of data might not be the best approach. So what we're going to focus on is allowing us to compare the building to its ideal performance or its current performance using simulation. So what we're going to do is we're going to gather, obviously, as much information as we can about the building, right? ASHRAE level to audit level things. We're going to try to get as much historical utility data as we can, whether that's from utility invoices or from Energy Star Portfolio Manager or other means and methods. We're going to take all of that information. We're going to create an operational model, is what we like to call it. And that operational model is going to simulate how the building is performing currently. Once we kind of have that baseline set, we're going to create an optimum model. And that optimum model is where we can kind of play with energy conservation measures, right? ECMs. And we can add insulation, we can add new windows, we can add air tightness, some of our other passive measures. We can replace mechanical systems, we can update lighting controls and things like that, and see what that does to overall building performance so that we can squeeze that last bit of energy efficiency out of that building pre-renewables. Once we have points A and B, now what we want to do is create a plan to get from A to B. Some buildings are vacant, and we can go right in and do the whole optimum model retrofit right there. Sometimes, many times, it's occupied, right? And so we've got to create a plan to get from our operational model to our optimum model, and that's where our decarbonization plan comes in. And after that, we can then bring in our data science, and we can deploy meters and sensors and just make sure that the performance that we had simulated is actually happening within the building, and we're not just giving them a plan and walking away.
Thanks, Matt. We're going to show everybody very shortly this item number 5, operationalize the performance model. We're going to show you that shortly towards the end of the presentation. But for the next bunch of slides, we're really going to focus on this concept of an operational model and the optimum model. To do this work, and we do these in these energy models, we're talking about them generically, but there are really 3 models that we do this work in normally. It's either going to be an IESVE, which is the Integrated Environmental Solutions Virtual Environment, or eQuest or Energy Plus. We call them 8760 models or hourly models. They're dynamic physics-based models. That's where this work can be done best in those 3. We also use subcomponent models. We'll use block models like PHVP and Wolfie Passive, and then we may even use some Flixo models to start vetting out some of our thermal bridging. But for the most part, This work can be done in the 8760 models. We do our work in ISBE because its capabilities are literally way better than the other 8760 models. So when you see these results and us talking about it, just know that we're in an ISBE model.
So let's dive into our project example, right? Our case study. So we've got a 500,000 square foot office building in Boston, okay? And it's going to be facing BERDO, which you're going to have to help me out, Craig.
I got it.
Okay.
It's Building Emissions Reductions and Disclosure Ordinance Act. Love our acronyms, and we're going to try to define them as we go through our presentations with you, but it's an acronym, and just think of it as their decarbonization legislation.
Sure. Thank you. It's a mouthful, and I was just going to fumble over it. So, okay. So what we've got is there are 3 tenant spaces within this office building. One of them is unoccupied, which is great, but kind of wish the whole building was unoccupied. That would be kind of very easy. Now some of the mechanicals are at end of life, so we're gonna have some triggers, some natural triggers for this building that might take our natural order of sustainability kind of out of sequence, and we're going to talk about that. And the reason we were approached to begin with is so that they can avoid fines, right? That's kind of the goal for the project, is to we want to be able to merge some natural triggers, but the overall goal here is we want to avoid any of those BERDO fines.
So Matt, when Beth and I wrote the book, we talk a lot about triggers and sequences. Can you do me a favor and just expand upon that a little bit just before we dive into it, so people just don't hear this word and not really kind of comprehend what is a trigger?
Yeah, so a trigger is any part throughout a building's life cycle that's going to naturally have to be addressed, right? Every aspect of a building has some sort of life cycle to it. Insulation can more or less last the life of a building, but when an older building maybe never deployed an air barrier. So if there is an opportunity to improve upon an aspect of a building while it's not being utilized or at its end of life, we want to make sure that we're replacing it with the optimum level of efficiency. And I say optimum because it doesn't necessarily have to be the most energy efficient thing that we can possibly get, because costs are involved in all of those things. So we want to go for the optimum level of performance. Now, when it comes to sequences, we also want to pay attention to combining some of these natural triggers with other aspects of the building, where we can get a larger bang for our buck than if we were to just do one or the other thing, right? If we combine more insulation with an air barrier, the overall building performance is going to improve more than if we were to just to do one or the other. So we're really looking for those 1 + 1 = 5, as you said earlier, items that we can really get that building to perform way better than it would otherwise.
Yeah, and we talk a lot about the triggers and the sequences in the book. Would it be fair, Matt, to basically classify triggers as life cycles, things break, deferred maintenance, we're already planning to do stuff anyways, natural renovations, any opportunity to touch the building, we would classify that as a trigger, right? That's an opportunity to do better.
Absolutely.
Don't replace in kind and expect a different result. And then the sequence is we cannot right size, quote unquote, our mechanical heating and cooling systems without first reducing our loads. Otherwise, we have an undersized heating and cooling system. So we have to respect the sequences while maximizing the opportunities of our triggers.
Right. And, just to take that one step further, we also want to pay attention to maybe the roof is at end of life. So we want to make sure that we add that insulation to the roof before we throw PV on it, right? If you start throwing PV on roofs just to get below fine levels, you're going to have to move that PV in 5 or 6 years when you replace the roof. So we want to pay attention to things like that as well.
Or you have the effect of doing what Beth and I always classify as immunizing your building, right? Because if you don't do that in the right trigger, you're just simply not going to do it. You lose that opportunity, and then you immunize the building over that life cycle, right?
Exactly.
All right, let's continue.
So we're gonna be taking a look at this chart here quite a bit throughout the presentation. This is going to kind of tell the story of our plan. What we're looking at is on the y-axis over here, we've got our site EUI, okay, and that's going to be in kBTU per square foot per year. And then we've got the age of the building all the way from 2005, when we could get the earliest utility data, all the way to 2050, when we'll say that the goal is to have every building in Massachusetts or in the Boston area decarbonized. Okay, so when we're looking at this, the purple line is going to show building EUI every year based on what we were able to get from previous utility data. And what we're trying to do is establish a baseline performance for this building so that we can create our simulated operational model. And so what we did is we noticed between the years 2013 and 2019 that the performance of this building kind of leveled off a little bit. Okay, that's about the best time worth of data that we can get for an occupied building, and how is it going to perform. So we took the utility data from 2013 to 2019, okay, and we created our average EUI off of that. Now, the reason we stopped in 2019 is, again, I mentioned earlier, the pandemic hit and people left the office. So we can see a steep drop off here in EUI, and you might look at that, and if you're comparing it to last year's energy, you're like, oh, look at that, we're already in EUI of 35. We're good to go until 2045. And that's not going to be the case, because you're not looking at the picture holistically. So we took the years 2013 to 2019, and we created our operational model. And so that's what these dotted lines are showing here. And so the building we're looking at is going to perform roughly at a 57, is about where this model is going to end up.
So, Matt, I think it's worth noting that the energy bill context that we're developing for this, we're doing it for the purposes of calibration within the model. And the information that we're using to do this is monthly invoices, because that's all we have at this time. And you can calibrate a model very well with monthly invoices. We prefer hourly meter and data sensor data, which would be more granular and a much better way to calibrate. But this works very, very well, right?
Absolutely. Yeah, this is, you can only model to what you know. And so what we know is we've got monthly utility data, and that's about as good as we can do. And like you said, if we had hourly, or we were able to deploy meters and sensors, we can certainly hone in on that accuracy of the model.
All right, well, let's see how you calibrated.
So what we're looking at here is our monthly EUI. So that's kBTU per square foot per month, not per year. And so in January, right, they were at a, I don't know, 5.8 or something like that. And so the blue line is showing what the utility bill average for that month was over that 7-year period. And the red line is where we were able to calibrate our IES-VE model to. And we're within 0.5% of what the actual building performance was. So we're always trying to strive for under 1% when we're getting into this, with the understanding that kind of industry standards are, as long as you're within 5% and 10% per month, we're within 10% on every month, we're good. So we like to be a little bit more granular than what the industry standard is looking for. Now, once we've established what our calibrated energy model is, we don't know the ratios of where all that energy is going in the building when we just look at monthly invoices. Okay, we don't know how much of that is heating. We don't know how much of that is cooling. We don't know how much of that is plug loads. But when we are able to get a calibrated energy model, we have a much better picture as to the pieces of the pie that are going to be worth going after for reaching our optimum model. And what we're seeing with this building is other processes, right? That's going to be plug loads, TV monitors, things like that, that are kind of driving the energy use within this building. Space cooling and space heating are obviously the measures that we want to go after from an energy performance perspective, but we also don't just want to focus our energy on the heating and cooling mechanical systems, because that's only going to get us so far. We're going to want to deploy things like motion sensors for lighting and some sort of plug load reduction strategy, okay, to help this building really get down to its optimum level of performance. And given that it's an office building, right, water heating is going to be, I mean, it's bathroom faucets is roughly all that they're using for water heating. So while there might be an opportunity to replace the water heater with a heat pump water heater, you're just not going to get that large of a return based on the overall energy use of this building. Okay, so now what we have is we've established our operational model. And so we're up here on the graph. Okay, now what we're going to do is we're going to deploy these passive, active, and renewables, the natural order of sustainability, to get from point A, which is where our operational model is, all the way down to B, which is where our optimum model can be. And that optimum model is going to include our passive, our active, and our renewables. Now, pre-renewables, we're able to get the building down to like a 27. Okay, so right about at where that line is about as far as we're going to get the building using passive and active ECMs. And then what we're going to do is we're going to give the client the overall picture as to what happens when they can deploy as many renewables as they can fit on the roof or nearby parking structures or things like that, right? So once we have our plan here from A to B, we also want to pay attention to regulations. Okay, and so this big black line that we're looking at is our step our step for BERDO regulation. So every 5 years, we're going to start in 2016, or I'm sorry, 2026. Okay, you need the EUI of this building to be below, I don't know, it looks like about 72, 73, something like that. Okay, and then every 5 years after that, the regulation gets tighter and tighter and tighter as we're on our path to a completely decarbonized building in 2050. Okay, so in order to avoid fines, I guess the short way of saying this, the way to avoid fines here is to just maintain our dashed line under the big black line. That's kind of the goal of this project.
So Matt, do me a favor. Can you walk me through the methodology of creating that big, ugly black line? Because the BERDO law is based on a penalty per metric ton of carbon per topology. And
Yeah.
how did you convert and get this into a BTU so that everyone could see it nice and clean against our project goals?
Yeah, no, that's a great question. Okay, so you're, like you said, for an office building, right, we're talking about an office building here. The levels are set, the step levels are going to be different than if this is a residential building or if this is a manufacturing facility or a hospital or something like that, right? The path to zero is just going to be a little bit different. And so what we need to do is two things are happening kind of simultaneously here. The building itself is getting more efficient by not using as much electricity, and that's where we kind of come in. But there's also this kind of assumption that is happening in the background that the grid itself is also decarbonizing, right? It's deploying more community solar arrays or implementing more wind power or other renewable ways to help generate electricity. So in our conversations with the regulatory people, they're saying, okay, so I don't know that we'll ever get to zero from a grid perspective, but we're going to get pretty close, and you can just assume it's going to be linear. And I think I kind of chuckled a little bit at that. So we assumed the grid is going to kind of have a curve, and I'm just going to draw here, that's going to look something like this. Okay, and this is going to be emissions per year. This is going to be CO2e, right? And so we're going to assume that the grid is going to get efficient. It's probably not ever going to get to zero. So in this conversion, right, it's a unit conversion from CO2e to kBTUs. We're assuming the grid is also kind of getting more energy efficient as well.
So at the end of the day, the black line is basically a mathematical derivative from the BERDO regulations to BTUs.
Yeah, I guess I could have just said that, huh?
But no, I mean, everyone sees these laws and they think they're so overly complex. And I just want to stress that this is just math, right?
Yeah, exactly. It's just math.
All right, let's pay attention to this chart here, because we're going to come back to this a handful of times over the presentation as we start to show you our strategies, because not everyone can do everything all at once. Sometimes we have to respect triggers and sequences, as we talked before. So let's talk about that.
So turns out finances are a thing, right? And they can't just throw all of the money at the building all at once, as much as from an energy modeling perspective and a performance perspective, we would like to see that. It's just not financially viable at this point. There are tenants, right? So what the plan that we kind of came up with based on triggers, sequences, and our natural order of sustainability, kind of melding all of those together, is in 2019, there's a natural trigger for RTUs. So what we're going to do is we're going to, at that point, separate mechanical systems, and we're going to have the RTUs only responsible for ventilation, and we're going to move to a heat pump heating and cooling system for the tenants. Okay, so we have a natural trigger in 2019. So that's going to make a small drop in our EUI at that point. We're also going to implement at the same time some passive ECMs, not all, right? But we're gonna implement the ones that we can implement, and that's going to keep us under that black line. And then in 2032, we're gonna have another natural trigger with some active ECMs, right? More efficient heating and cooling equipment. The heating and cooling equipment that we didn't address in 2019 is going to be at end of life, so we're going to address it at that point. And then in 2043, we kind of start seeing some more triggers, okay? And that's going to open up, right? We've got lease expiring and things like that, where we'll be able to get into the units and deploy some more passive ECMs to help get us below that final kind of curve in 2045. And then in 2045, 2046, we can deploy renewables at that time. And so we'll also have a better picture of how clean the grid is at that point, and how many renewables we need to do, more efficient solar panels, right? Who knows where we're going to be in 2046, but that'll be the time that we want to deploy those renewables to get us as close to zero as we can by 2050.
So if our clients have the sole goal of not paying any fines, we can use technology to basically create a plan, a phased plan on how to execute. Now, Matt, this arc that we see here under that blue line, is that the same arc I'm seeing right here?
The path, so if we just leave it there for just a second. So again, we're starting at A, and B is actually down here, right? We want B to be zero at 2050. And so if you go to the next slide, it's just we're taking a different path using triggers and sequences instead of just going like that.
So would it be fair to say that when we develop the operational model, which is calibrated against the building, that is our tool to test? And when we create an optimum model, we're saying, what's everything I could possibly do to build the best building we can build pre-renewables, and then offset as much as I can based on what's available. So we're executing everything and we're simply phasing it out, as opposed to going in and saying, okay, there are some additional constraints. Maybe our client doesn't have a trigger of replacing, say, windows, and they want to push that along. We can then phase back the solutions and do something shorter than an optimum and still plan that out. So when you hit that B way out in 2050,
Yep,
we're still doing the right thing, right? Is that
exactly.
the purposes of a
might
decarb
just
plan?
be up a little bit higher if for some reason one of those ECMs isn't accepted for whatever reason.
Exactly. So the point we're making here is that know where you can go, and then use your triggers and finances to plan that until you get there and you have time to do it.
Exactly.
All right.
Okay, so what we've got here is a really cool graph. What we're looking at here is our overall energy cost, and our dotted line is kind of showing this curved line is kind of showing business as usual, right? If we don't do anything to the building and we're just going to say, yeah, whatever, we'll just pay the fines and put it onto the tenants and just kind of make it, like I said, business as usual. That's roughly what we're going to see in terms of energy performance. And we're assuming about a 4 to 4.5% increase in electrical usage over the course of this time period. Okay. Which is why it's not just a linear line. So this solid blue line that we're looking at is going to line up perfectly with our
Can I show it?
decarbonization plan. Yeah, go ahead and just go back.
So look at the arc here of this, right? And
Yep.
what we're saying is that arc is this arc.
That is that arc. And now we're just looking at it in dollars instead of kBTU. Okay. And so the difference between business as usual and the decarbonization plan that we've shown is going to be our 27-year projected energy savings, which comes out in this case to be $55.6 million. Now, conversely, if we were to just deploy the optimum model at day one, right, in 2026 or something like that, the solid blue line would look something like, look at that, nice straight line, something like that. And then our delta would be between this dotted blue line and the solid red line that I just drew. And we could actually show a whole building projected savings of like $98 million, something along those lines.
Would it be fair to say that that dotted blue line, the first arc way up there, that is our operational model? And
Yes,
then the arc below it is the optimum model?
Exactly.
And that optimum model, again, we want to show what we can do so our clients have the full value of information on performance, and then they make the decisions on how to phase that in.
Exactly.
This is much different than incrementalism, right? Incrementalism is doing one thing at a time and not really understanding its impacts on everything else in the building.
Right.
So guys, let me ask you this question. So when a building owner's thinking about renovating an existing building, we often talk about no regrets moves, right? And so isn't one question that most people should ask that they don't ask, that is entirely a no regrets move? What is my building capable of achieving, right? Instead of how do we incrementally improve the building over time? What's it capable of achieving? And isn't that what we call the optimum decarbonization potential of a building?
Yes, absolutely, Beth. You nailed it. Yeah, we always should be asking what is the most, where can we get this building to perform, right?
What's possible,
What's
irrespective of what you might want to do in what order or how much you might want to spend. Know what the building's capable of achieving. So if there's one no regrets move that anybody watching this webinar walks away with, is if you have an existing building, you're going to renovate it, the first question you ask any engineering team or any project team is, what is my building capable of achieving? And know that answer before you make any moves.
Absolutely. Because with an existing building, right, we're kind of stuck with orientation, right? We're kind of stuck, unless you're repurposing the building with window to wall ratio, right? You're kind of stuck with geometry. So there's only so much that you can do. So maybe your optimum model doesn't get to zero. Maybe it does, but every building is going to be different. And it's really important to identify where your building can get to.
And Beth, I would add one more thing to that analysis, is that Matt and I frequently use the term pre-renewables. And the reason why we do that is because we want to make sure we understand what that optimum level of performance is before I apply renewables. If not, it skews the question, right? Because if we understand the answer to the question, how good can we be pre-renewables? That's the efficiency angle here, where the cheapest form of energy is the energy we never spend. Plus, my PV array becomes smaller and more affordable. When I have to replace it in 10 or 20 years, it's cheaper and easier to replace that PV array. So again, we always stress, separate and bifurcate your pre-renewable strategy with your renewable strategy. You can execute both, but know the answer, because that's how you create a plan.
And Matt, that's what you're showing right there.
That's exactly what I'm showing right there, is the deploying energy efficiency measures is going to get you everything up here, and renewables is going to get you the things down here. So you can usually, right, for this building, achieve far more energy savings by doing passive active natural order first and then deploying renewables.
Great. Thanks, guys.
Yeah, and Matt, as you just showed right there, you win when your operational model becomes your optimum model, right? And that's how it continues to operate until you hit that optimum model. Then you don't need two models. You've done it. You've hit it. And what happens when we do that, right? How do we use an operational model? Well, this gets us into our next slide here. And this slide here shows these big blue bars are meters, and the green line is simulation. And what we need to really convey to the audience here is that we can take from our physics-based modeling hourly data, hourly simulated data for future performance. I can do that against all forms of energy for energy consumption, gas, electric, district energy, PV. We can simulate all of that. We can also simulate temperature, humidity, and CO2 by zone. Anywhere you can put a meter, we can create a virtual zone and export that data. And we can also do it for BAS parameters. BAS is the building automation system, or temperature controls. And we can export all that and provide all that data into the dashboard technologies that are in buildings today. And that gives you a higher level of context. So now we understand, and we can answer those questions for owners. Did we get what we paid for? Are we winning or losing? We need to know that answer, because our owners are investing in these buildings and they're expecting an ROI, and they can't wait 12 months for invoices to determine whether or not the building's performing as intended. So we can then take this and integrate it right back into the technology, and that's exactly what we're talking about. With that, this is the information for Matt and myself. Feel free to reach out to us if you have any questions at all. Beth, there were some questions that came up in the presentation we had yesterday. Did we cover all those today in this presentation, or did we miss anything?
No, we did. We mostly hit them. There was a discussion on return on investment and how do we do NPV calculations and ROI calculations for clients. And the answer we gave to that is, in most cases, we don't, because our developer clients generally want to do that work themselves. They want to make their assumptions. Each developer, each building owner has a different timeline. And the assumptions that they'll embed in their NPV, while we can do a simple NPV, it does not get it nearly the level of complexity that most developers have when they look at whether to hold an asset, buy an asset, sell an asset. The other thing that came up, I think, in the discussion too, is the idea that a decarbonization plan and understanding what a building's capable of achieving is soon going to become kind of expected, much like how a developer would present a pro forma to a prospective buyer, or if they are selling an asset, they're going to need to present a decarbonization plan at the same time. And so the work to go through this effort to have this is probably just the right investment. The other no regrets move, I think, Craig, that we made a pretty big deal out of that maybe we didn't spend as much time on today, is the idea that when you get a physics-based model and simulation of a building that demonstrates its optimum decarbonization potential, you want those files. You want that piece of collateral, or that piece of, or that asset. You want that asset. You want to own that asset. So don't just accept the report. Make sure you get the originated files, or whatever you can, because that should live with the building for its life. It should always be available to the owner to give to any project team who might touch that building over the course of that building's life. So those were the three things I kind of wrote down that we covered off in a little bit more detail with the team.
No, that's awesome. Let me, I have to add a couple comments to two of those things. So Matt, I've hung out here on this projected savings chart here, and there are a couple assumptions that we use to get here. Can you walk us through those two assumptions real quick?
Yeah, absolutely. So the first assumption obviously is cost of electricity. In this case, the building is all electric already. So the cost of electricity is going to increase at a rate of 4 to 4.5%, which is what the average rate of increase of electricity has been And that might even be, at least in this location, that might even be conservative as the utility invests more and more in more infrastructure for renewables, right? As they need to get cleaner and cleaner and cleaner. So that electric rate might actually go higher, which is going to end up showing a bigger rate of, or a bigger overall energy savings. Okay. And the other thing that we're kind of assuming in this is the grid is getting cleaner and cleaner and cleaner throughout the whole process. Okay. So that while the grid, the emissions of the building might go, the overall emissions that we're looking at might be going down, the energy savings, right? The dollars is only going to go up.
So
Those are kind of
basically, the
two
point
things.
is that these are very conservative assumptions in terms of predictions of what's going to happen in the future. And it's done purposefully because, to Beth's point, we want our clients to be able to do that math. If they're going to trust it, they're going to run their own ROIs or net present value calculations to determine if this is a viable investment for them into the buildings. So what we do is we take a super conservative approach to this. And also, Beth, we're not putting any value in this for occupant benefit, asset valuation, any of those, what we would refer to as a relatively soft cost. We would all collectively agree that the number is greater than zero, but we let our owners basically apply the value of that. And we're just looking at straight savings. That's as simple as this is. So anyone who wants to argue that the envelopes don't pay clearly hasn't done the math yet.
Right. So anything else? I think we're about at our time commitment.
Yeah, one other thing, Beth, you had mentioned the model in retaining the originated files from the model. What you'll notice here in our optimum plan, our decarbonization plan, is some of these activities could be pushed out years. And when they're pushed out years like this, chances are you're going to be bringing in an architectural or mechanical team that may not be familiar with the decarbonization plan. And much like the building information model or your BIMs, you want to be able to give your teams the background drawings in AutoCAD or Revit. You want to be able to give them the building energy models, the originated files, because you don't want to have to repay for that. You've already paid for it once. So to Beth's point, get yourself a BEM execution plan. Make sure you retain the original copies of these files and use them throughout the life of the building. You can use them to update future plans of decarbonization, and you can also use them to operationalize your model. So
Yep.
with that, those are the two things I wanted to add.
Go flash the last slide real quickly for anybody who missed it and didn't get a chance to get your contact information.
Oh, I'm sorry. Thank you.
Go to that in case anybody wants to take one last picture. Otherwise, we are going to sign off. Thank you again to 3C Ren, Passive House California, and Jay Gentry himself. We appreciate the opportunity to put this together for y'all and hope you find it beneficial. Have a great day.
Thanks, everyone.
Thanks, everybody.